So, in this example, even though we know there's going to be oxygen, which is going to make things a little bit different than that first example, we still start the same way, finding the oxidation number of our elements so that we can split our reactions into half reactions. Remember, things like I minus 1 label themselves. It's a minus 1. This I is a 0. So we can already tell that it's being oxidized. It's going up in oxidation number, which means the N is going to be the thing being reduced. From here on out, oxygen is just going to be along for the ride. It's not going to be the thing being oxidized or reduced. But if you're in any doubt, we can dig into this compound and figure out what that oxidation number is of that nitrogen. But really at this level, we're just using those oxidation numbers to split things in half. Now, this NO is easy enough. Start with the O, it gets a -2. Nitrogen balances it out with a +2. Here we give oxygen what it wants, -2. But since we have 2 of them, keep in mind that's going to be a total -4 charge here. And because the NO2 molecule, nitrite ion really, has a total -1 as its oxidation number, then nitrogen's oxidation number plus the -4 from those 2 oxygens will get us -1. And +3 is the number. That +3 minus 4 gets us -1. So that does confirm that our nitrogen here is being reduced because it's going from a +3 to a +2. It is going down. So let's split apart our iodine and nitrogen stuff, and that oxygen stuff is just going to stay with our nitrogen. So we have split our reaction to half reactions, and I've done that in red there, just trying to keep track of my colors. Now we still pay attention to the special elements being oxidized and reduced, just the iodine and the nitrogen for now. We're going to take care of that oxygen by adding waters in a second. So our iodine is the one that we need to balance because we just had 1 I here and 2 over there. Our nitrogens are balanced. There's 1 N on each side. So those are good. We're not going to use any coefficients in that second half reaction yet, because the O's are the only part that's different. And honestly, let me use a highlighter just to show you. If I tried to fix my O's by putting a 2 here, that would get me 2 O's, but it would also get me 2 N's. So you might think, okay, well, put a 2 here. Well, that gets me 2 N's, but now it's 4 O's. There is no number that we can put in front of either of these in order to get the N's and O's balanced. We have to balance it another way. So we're going to do that by adding water, H2O, to the side that needs more oxygen. Since we've got 2 oxygens here and just 1 here, we need to add 1 H2O to this side so we get that 1 more oxygen. But along with that 1 oxygen we were trying to add came 2 hydrogens that we didn't really expect to add. But we're going to take care of that in this next step. Anytime we add water, H2O, in order to get the oxygens, we have to balance out those H's by adding H pluses to the opposite side. And it's always going to be twice as many H pluses, because for every 1 H2O we add, we're adding 2 H's. But basically, however many H's we add to one side, we have to add to the other, keeping things balanced. So now we need to look at the charges and try and balance our electrons. I'm actually going to do this in blue, or balance the charges with electrons. So remember, we're adding our electrons to the product side of oxidation. They're always coming out, being lost from our oxidation half reaction. And as I'm asking myself how many electrons I need to add, remember, we're trying to make the total charge equal to the charge we already have on the reactant side, which is currently a -2 from those 2 I minuses. So we need to add 2 electrons. I know so far it's basically always been 2, but it's not always 2. And down here in our reduction half, we are putting our electrons on the reactant side. And if we're adding our electrons to that reactant side, we're trying to match the charge that we have on the product side, which is 0. So we're trying to bring this side's total charge down to 0. And currently we have a -1 and 2 plus 1s. So our current charge on this side is a +1, plus 2 minus 1. So we need to add one more electron to this side to bring that total charge down to 0. So we have balanced the charges within each of these separate half reactions by adding their correct number of electrons. But as we know and have seen from previous problems, we have to have our electrons equal, because these are the 2 electrons being lost, and it's the same electrons being gained in this reaction. But right now, it looks like we've got some magically disappearing electrons, which can't happen. We need to gain 2 electrons if we were losing 2 electrons. So the way to fix this is by multiplying that reduction half reaction by 2. And we can't just multiply the electrons by 2. We have to multiply everything in that reaction by 2. And once again, I'm just going to switch colors so you can keep track of where these numbers came from. So we're just going to multiply everything by 2. Because if I want this reaction to be able to take twice as many electrons, I need to have twice as much stuff in it that can take electrons. So our H pluses become 4 H pluses, and then 2 NO2 minuses, 2 NOs, and 2 H2Os. And now, as soon as our electrons are equal, and they're on opposite sides, they cancel out, and everything else that was left behind on that reactant side is coming down to the reactant side of our overall. And you know that everything left behind and not canceled out on our product side is going to be coming down to the product side of our overall. So I'm going to write that carefully. And that is our final overall. A little bit bigger and more complicated than that original equation, and you probably would not have been able to balance it without using this process. So I know the oxygen ones are a little weird, but it's really not that hard, not that impossible. So let's look at the next one.